So last time we were doing two equations we did. One was conservation of mass, which is called continuity equation, and the second one was conservation of momentum. Okay, and the conservation of momentum had three components: x direction, y direction, and z direction. Now we are doing conservation of energy equation. Okay, again, as we did last time, first we talk about the physical law. Physical law is conservation of energy. Okay, now how do we do it? That we first consider a control mass system. Recall that we have done, when we were talking about continuity equation, we had taken control mass system. When we talked about momentum equation, we had taken control volume system. Now again we are taking control mass system. Okay, and it is up to us. There is nothing special about it. It is a question of convenience. Okay, now this is our control mass. Okay, it has as I told you, it has flexible boundaries but impervious. Why flexible? Because its shape as well as volume can change. Both these can change. And when we talk about impervious, which means delta M equal to 0. Mass remains constant. Okay. Now, if we talk about energy balance of this, let us see what will be the change in energy in the system. There is one energy which is in the form of work. This is W, the amount of work done on the system. Now here it is taken as positive, unlike in thermodynamics, where the work done by the system is taken as positive. There the objective is that we want to get work out of the system. We are talking about engine primarily, that is the issue, and that is why traditionally we take in thermodynamics work done by the system as positive. Now here we are talking about work done on the system as positive, the amount of energy going in. Okay, then QC is the amount of heat conducted in. What is the amount of heat entering in? And QG is the amount of heat generated within. Now this generation can be because of number of things. One is because of viscosity. This generation may take place because it's all moving, velocity is there, viscous forces are there, kinetic energy can get converted into heat. That is one way. The second is you can have a chemical reaction which may generate heat, right? And we can also take something like, you can talk about electrical heating, right? And then there is one more, the radiations being absorbed. Now it is up to us, absorbed, that how do we want to take the radiation. We can take it as the radiation coming from outside, then we have to add it here, okay, QR, or we can take it here, then it is being absorbed. It's up to us. Okay, so it depends how do we take it? Only thing we have to see that the energy coming from outside is positive. Okay. Now, what will be the rate of change of energy? This will be, you sum it up all and find the derivative. Can you think of any other energy? You have a control mass system, right? It's a fluid. Can there be any other energy? Kinetic energy. Kinetic energy बाहर से थोड़ी आ सकती, नहीं आ सकती ना. अंदर की kinetic energy is here. It is already here. It's a impervious system. Nothing can come out from outside. So nothing can flow in with the mass. Right? Kinetic energy, if it has to go in, it has to come through mass, but the mass cannot enter in. So kinetic energy cannot enter in. Yes, anything else? There is one more, that is potential energy. Once we talked about kinetic energy, we can also talk about potential energy, mgh, right? Potential energy. That is also part of here, mgh. But we normally do not take it, because potential energy through gravity is not much. And if it is, we have to take it. That we have to decide. The equation we are doing, we are not talking about potential energy, but we can very well, and it should be counted. Why we are not counting it at the moment? Because we think that it is negligible. Okay, but it is very much there. But you can say that we will be doing body forces, work done by the body forces, that will take care of this. Work done by body forces. So it will come there. So I was wrong that it is not there, it is there in this. Coming as potential energy, work done by the body force. And body force is, at least in this case, is gravity. Okay. So now let us move ahead. What are these terms? W dot is the rate of work done on the fluid element by external forces. That is the work done by external forces. Now Q dot has two components. One is the conduction, one is the heat generation. So Q dot C is the heat conducted into the fluid element, and Q dot G is the rate of heat generated within the fluid element. Okay. Now then we have said that heat generated may be through chemical reaction, flow of current, or absorption of radiations. Okay. When we talk about viscous forces, this is a conversion of kinetic energy into heat, right? So it will not be there, because we are already considering the kinetic energy. Whatever the change in kinetic energy will come here, that has gone as heat. Okay, so it is not needed. Okay. Note that there is no convection of heat. Okay, we have not considered convection of heat, and the reason being that convection is carried by the mass. As no mass is entering in, no convection of heat will take place. Okay, it's a control mass system. Now let us proceed further. Now first what we are doing is we are writing forces in x direction. Again, we are doing it just to save our space and the confusion. So first we talk about the shear forces, and all these forces we have already talked about, right? A, B, C, D, and there will be E, F also and G, H also, but they will not be shear forces. So these are the shear forces. Okay, and you can see here they are here. A is here, B is here, C is here, D is here. We are considering only in X direction. Rest all we will add up. Okay. Now these forces, these are the normal forces we have. One as a component of shear tensor, okay, and one as a pressure, and they will be normal. We are talking about X direction. Okay, so this is a shear force, 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 this is normal, this is normal, this is normal, and this is normal. Okay, so we have taken only 4 as the shear force. Okay, okay, now we are talking about these normal forces, these E and F. These E and F, these are the normal forces. Then the pressure forces, G and H, and then the body force. Okay, it is all already we have discussed. Now, what is the rate of work done on the fluid element by all these forces? So what we are doing it, we are dividing in 3 parts. All these forces, the body force will do the work, surface force will do the work, pressure force will do the work. Okay, but we will do them separately. So this is the rate work done by the body force, work done by the surface forces, and these are the work done by the pressure forces. And surface forces include your tau I, j. Also there are total 9. Okay, it has shear plus normal. And because normal forces will not be there, you can put that tau xx, tau yy, tau zz as 0. Okay? That is, we can do it. Why we are doing so? Because of generalization. Okay, so your normal force tau xx, comma tau yy, comma tau zz, they will be equal to 0 for the fluid. Okay, now this is the work done by the body force. First we start with this. F is the body force, and normally it is G. And I told you it can be magnetic force also, electric force also. If your fluid is charged, you can have magnetic force also, and if it is flowing and charged, you can have magnetic force on this also. Okay, so we can have B also here, we can have E also here. Okay, so one is the gravitational field, second is the magnetic field, third is the electric field. All of them can be there. Okay, so you multiply force with velocity, that is the work done, and because this force is F is per unit mass. F is the body force per unit mass, so you multiply with rho and delta V. Okay. Now rate of work done by surface forces. Now what we are doing, we are taking only 2 forces, and we know there are 2, 2, 4 and 2, 6. 6 of them are there. Okay. So in X direction, these are the 2 we are taking, and we are talking about the plane only in k direction. So the one will be the bottom plane, the second is the top plane. Okay, so this tau ki is the first component is direction of plane, and the second component is direction of force. Okay, now so we will be using these conventions that xi, if you put a cap on this, it's a I vector, and it is also written as x vector, xj, j or y, xk, k or z. You can use any one of them. This is the normal practice to use it. Okay, now what we are doing, we are calculating work done by surface force, only two forces which are in direction k and which are acting on plane k and in direction I. Okay, now so this is written as ki, tau ki. Now if we want to find out the work done, you have to multiply the force with velocity. Okay, so at the moment it is telling you only work done per unit area, so we have to find per unit volume. Okay, so what you do, on the top plane, this is your top plane, the work done is you multiply the velocity in the x direction with the force in x direction. Okay, you get the rate of work done, and obviously it has to be multiplied by del y and del z. Sorry, it is del x. Z direction में जो plane होगा, that will be having area equal to del y into del z. Okay, so you have to multiply shear force by area, and this can be written as, so this is the bottom plane, and the lower one is this is the bottom plane, and the lower one is the top plane. Now this thing can be broken into four components, as we were doing last time also. One term 2 and 3 are added here, and the fourth term is here. So you multiply 2 by 2, you get 4 terms, and out of that this term is approximately equal to 0 because there are double differential element. Okay, in all the other you will find only one is there. Okay, so they become equal to 0. Now when you subtract these two, because one will be the force working against and one will be working in, so one will be the work going in, one will be the work going out. The difference between the two will be, so this is one which is I think going in. No, you have force will be here and the velocity will be here. This will be okay, and this will be the one we can see. Yeah, the top one is one which is going in, right? Your force is moving along the direction of velocity. The bottom one is one which is coming out of the control volume. Control volume is doing work on the other fluid, outside fluid. Okay, so the difference of the two will be equal to this, and this is SKI, work done by surface force, and the surface force is one which is acting on plane K in direction I. Now you multiply it by, your multiplication by volume is already come, because these are the shear forces. You will multiply them by this component. This is nothing but delta y and delta x. Okay, your force is working on plane K. So what do you get? You get this term, and this is for only when K is equal to 3 or I is equal to 1 or Z plane X direction. You take all of them together, you get this. So what you have to do, just you have to change I to ijk and j to again jki. You will get 9 forces, 9 terms. Okay, so this is one. Then the work done by pressure. So this is work done by body forces. Okay, then we talk about this. Let's first calculate the work done by pressure acting in x direction. So we are only talking about x direction. Then we'll add all the 3 directions, we'll get the total work done by pressure. So the work done by pressure is pressure force multiplied by area multiplied by velocity, right? This will be on the right hand side. So pressure is working on the right hand side. Because the velocity is positive direction, this work is minus. So the pressure on the right face is doing negative work. It is extracting work. Pressure on the left face is in the direction of velocity. So it is working positive work into the system. Again, you will add them up and you'll get work done by pressure in x direction. These will be the terms, and you can add it up like this. You will get this. So there will be 4 terms for this, right? Which will be equal to 1 plus 2, 1, 2 plus 3 plus 4. This will be equal to 0. This will cancel out with this. Okay, and these two actually come up here. That you should do it by yourself so that you know. A standard thing, we will be doing it many a times. Okay, now what you do, you add up for x, y, z. So what you will get, you do this, you keep changing x to y, then x to z, u to v, and v to w. You get this. Okay, so this is the work done by the pressure forces, and it can be written conveniently. This is our form of gradient, divergence of P into V. Okay, now then, so what we have found out? We have found out work done by body forces, work done by surface forces, work done by pressure forces, and we are finding the total work done by all the forces acting on the system. You sum it up, you get this equation. Okay. Now, then this is your body force. We have done it. Body force. This is the shear force, and this is the pressure. 3 terms. Okay, they are put together. Now the rate of heat being added to the fluid element. Okay, again there are 2 components. One is the heat being conducted in, and one is called the heat generated inside. Okay. Now heat being conducted in is actually a diffusion process. So we will talk about this later on. So there are two ways in which the heat enters in or comes out. One is through convection, when the mass also flows in or out. The second is your diffusion, when because of temperature gradient heat flows in or out. Okay, so this is a diffusive process. Diffusive process, even if you have fixed boundaries, fixed in the sense impervious boundaries, diffusion will take place, because you are not allowing mass to go in, but energy can flow in and out. Okay? So again I am highlighting here, there is no convection heat flow, as it is a controlled mass system. We are not talking about convection heat flow. Okay, now how do we find it? You have a body here. Now temperature is increasing left to right. Temperature is increasing left to right. So you keep a cube. On the left side, the temperature is higher on the right side, so the heat will flow out. On the right face, temperature is higher outside, because temperature is increasing left to right. This cube will be inside. So from the right side, heat is entering in. From the left side, heat is entering, exiting, coming out. Okay. Now that you can write. Again we will talk about only x direction. So this is the heat entering from the right plane, and we have that Fourier's law. Okay, what is the rate of heat, temperature gradient multiplied by k delta T by delta, and this is on the left plane. On the right plane, what is happening is your temperature gradient is changing. Whatever is the temperature gradient on the left plane, that changes on the right plane. So that is why we have this term also. Okay. So if you let me just write here, on the left side the temperature gradient it is this. On the right side the temperature gradient is this, plus del square T by del x square into delta x. So there are two different temperature gradients, one on the left side, one on the right side. They are not same. Everything is changing as you move along the direction as well as time. Okay. Now if you solve this, you get this, because this will cancel out with this. So this is what is left, and then you can add all the planes x, y and z, you will get this. You add all of them, you get these three. These are the three components of heat flowing into the body from x, y and z direction. Okay, which can be written like this. All of them put together can be written like this. It is divergence of k into gradient of T. Gradient of T tells you the rate of change of temperature, the not rate, how the temperature is changing with distance. K multiplied gives you heat flow, and then you and the divergence tell you the difference between left and right. Okay. Now then heat generated within the system is given by this. Is you have the volume here, volume into mass, density into volume gives you mass, and this is the, so you know what is the rate of heat generation per unit volume or per unit mass, and so Qs is the rate of heat generated within the fluid element per unit mass and multiplied by mass. Okay, and this can be through chemical reaction or radiation. Viscosity we will not talk about because viscosity is taken care of in velocity. What is happening? The velocity, kinetic energy is reducing and the heat is being generated, right? So it is already being taken care of. So now the total heat input is equal to this two terms. Okay. Now our element is delta VL having a density rho, right? Total mass आ जाएगा rho delta VL, and this is the energy within the system. Okay. Now this energy has two components. One is the specific internal energy of the fluid element, which is based on temperature. The mass can store some energy. And the second is the velocity, the kinetic energy of the fluid element. Is there any other energy? No. Okay. So now this total energy actually should also contain gravitational the potential energy इसको होते हैं, because this is total energy of the fluid element. Okay. Now what we do, we find the derivative of this. So we will get rate of change of energy. So what is the rate of change of energy of the control mass? Is the amount of energy which is going in plus the amount of energy which is generated in. Okay. Now we have considered the fluid element as a control mass system. For a control mass system, mass is conserved, therefore m is equal to rho delta L is constant. So when you find the derivative of these terms, these two terms will come out as it is. So what is left is this. Inside the derivative. Now then we write energy equation in form 1. So we have calculated all the forms of energy and left hand side as well as right hand side. So we can say the change in energy of the control mass system is equal to the amount of work done by the external forces plus the amount of heat generated within the system or entering from outside the system. Okay. Now we know that W is equal to this. Already we have done above. We know that Q is equal to this. We have done above. So this will be equal to this. This is our equation of energy. Left side is the rate of change of energy within the control mass, and see that everywhere delta VL has cancelled out. It was there in each the term, it has been cancelled out. Okay. Now I have named as A1, B1, C1, D1 and E1 because we will be doing jugglery with them one by one. Okay. So we are doing it. Now we modify this equation. Okay. Modify means to simplify it. We are simplifying it. Now what we are doing is that this equation, this 627, by removing the term this from either side of the equation. So you can see that this term is on there, we are talking about this term, but it is not there on the right side. but it is, we will find out it is there. So, and then we will cancel it out. So our equation will become a bit more crispy, shorter. Okay. So what we do, we can write this term. Now focus on this term, rho d by dt of half v square. We can write it like this. So now I am showing just the mathematics, how we can do it. You have this term here, okay. Now this v is nothing but summation of three velocities. This v is vector. Here it is where every v is vector here in this. We have combined all the things, all the three vector form, okay. But this is a v square, so v square is a scalar, and v square is equal to sum of u square v square plus w square, okay, kinetic energy. Now you know that this derivative is equal to this much, okay. U into u, find out the derivative, it will be equal to 2u du by dt, and there is a half, it will cancel, so you will get this. So what do you get? That this is nothing but equal to this. And then you can write it like this. So both left and right are same. No physics. Simple mathematics. Okay. Now this term is there on the right side. Let's see, it is there. It is here in this. Again there will be two components of this. Two things are inside the derivative. You will do first multiply by derivative of 2 plus second multiply by derivative of 1. So, okay. Now, finding this term from momentum equation. So, this is the term we will find. Sorry, we are trying this term from momentum equation. Okay. So we already know this momentum equation. This is all the terms put together, or all the three equations of momentum equation put together. Now what do? We take x component of it. We know this equation, momentum equation. X component of it multiplied by u on both the sides, you get this. Similarly, what you can do, you can now obtain other two equations. So I have not written here, but you can do that. And when you add up, you get this. Right? So now again we have this two identities we will be using in this. One is this was the term I was talking about. You can break it in two parts. Similarly, this one can be broken up into two parts. Okay, and that is what we will be filling it up here. So Now this is the original equation I was talking about to you, energy equation, three components. And now this equation here, this one, which one? Yeah, this one, right? 34. Okay, this is the 634 equation, which is written as 638, and this is 627 equation, which we have written as 637. Okay. Now what we do, we will subtract from A1, A2 we will subtract. Now remember, your A1 is made of two components. This is one term and this is nothing but A2. So what we are doing is, once you subtract from A1 you subtract A2, you get this term. A1 से आप A2 सब्ट्रैक्ट करेंगे तो आपके पास ये आ जाएगा टर्म. ठीक है, दिस इज A. You get A when you subtract from A1, you subtract this. Okay. Now, so what you have done, you have subtracted from this, you have to subtract this. Now, this will remain as it is, B term will remain as it is. This is your B term. So B1 comes as B. B1 and B are same. Now C1 and C2, this is your C2 here, right? You are subtracting C2 from C1, you get this. Okay, there are this. Okay, this is the momentum equation and this is the energy equation. So energy equation का जो term C1 है, उसमें से मोमेंटम इक्वेशन का टर्म C2 हम सब्ट्रैक्ट कर देंगे. इसमें दो टर्म्स हैं. ओके, सो वंस यू डू इट, सो यू गेट C1 minus C2. And similarly from D1 you are going to subtract D2. Once you subtract D1 from D2, you get this term. Okay, because there are two terms here. There are two terms here, two terms here. Okay, and these two terms are same, E1 and E2. So you get E1 minus E2 equal to 0. So what basically you have done is, this is your energy equation. Okay, on the left side you have broken into two parts. Okay, then momentum equation you have multiplied by first equation, x direction equation by u, y direction by v, and w direction by z direction by w. Okay, so now what we are doing, you are subtracting from energy equation momentum equation multiplied by velocity, and that you can do. Energy is mv square, momentum is mv, you multiply it by velocity, it becomes energy. So you are subtracting energy from energy. Okay, of course momentum, when you multiply by velocity, it will not be called energy. It is the force multiplied by velocity is the work done. Okay, so but because momentum equation is anyway valid, you can apply that. And what do you get? You get this. This is the equation. So this is your equation for energy. Okay, now look at this equation. This is the equation in a non-conservative form. And where is the non-conservative component? It is here. You can change it again as we have done before, right? This is the mathematics is just telling you about the phi. You apply it to this. You can write the same total derivative, local derivative, and convective derivative. This equation is for your general phi parameter, You remember here, this is the equation for total, local and convective derivative, and you are multiplying it by rho here. Okay, multiplying by rho, and then this is your continuity equation. You make it equal to 0. Okay, so you get this. Now phi you can replace by E, you get this equation. So rho dE by dt can be changed into these two terms, and you get this equation. This is a energy equation in conservative form. Okay, get it. Now there is one more small thing to be added here. Now when we are talking about heat conduction, when we are talking about heat conduction, it is quite possible that conductivity may be different in different directions, right? If that is the case, you have to talk about Kx, Ky and Kz. And this equation remains same which we had written in energy. Only thing is now K is having, it's a vector form, or you can say it has three components, Kx, Ky and Kz, and it comes inside the derivative, divergence. Before the gradient, after the divergence, you can see this is the equation. This is basically, you know, this is the equation for heat transfer in x direction. Only thing is now I am saying that Kx, Ky and Kz are different. Okay, so what you will do, this is written in this form here because gradient is three components, you will multiply with K, Kx, Ky, Kz, so you will get the same equation. Okay, but normally a fluid would be isotropic. In all the direction it will be same, right? So you can have, if it is anisotropic, Kx, Ky and Kz will not be same, right? But if it is isotropic, you will have Kx, Ky and Kz will be same, right? And note that the fluid we are talking about are isotropic material because they mix in the reactor. But still it is possible that you are having fluid mixing in such a way that they have different formation in different directions, then you will have to take care of that. So this is what is your energy equation.